Hello everyone, so this is Paulo AI again, and we are going to do tutorial number 5, JEPA. Because in the previous one, what we did was to essentially train a model on 3 different datasets. We play with dimensions, try to kind of identify what was the best dimension for the latent variable. And we try different seeding strategies, different activation functions, and then essentially we save them into checkpoints. So the idea now is, well, what do we do with these checkpoints? And let's suppose we essentially we want to essentially train this. So what we're going to do here, so we are going to reload them from the previous session. We want to run inference on new unseen inputs. And we're just going to explain what you need at runtime or inference time. And what sort of sanity checks you have to do, maybe confidence, energy scores. And for example, then can you do some sort of downstream task like classification using these latent vectors? Okay, so what do you need at inference time? Well, you need the same transformation as training. You have to do a Fisher transform. It's pretty much like any other machine learning pipeline. So you have to remember what kind of processing you have done. So the transformations, you have to apply the same scalar statistics like mean and scale from training. And you have to keep the encoder. So if you never throw away your encoder, because that's the basic thing you need. At minimum, you need to have an encoder. And what you usually don't need is the encoder for Y, unless you're doing things like video prediction, I think, and the predictor branch. So you actually can throw them away. I mean, don't throw them away, save them somewhere. But in general, for the simplest case, you just need to use the encoder. And the other ones, you can keep them on disk. And so in terms of energy, so we use this energy style confidence defined as the distance in latent space to class prototypes. Okay. So essentially the energy of x in this case is the minimum square distance from z of x to class prototypes. So lower means closer to known latent regions, because we can recover it from, we know the data set, right? And higher means potentially uncertain or out of distribution. So the idea is to, essentially, lower means more in distribution, more confident. Higher means out of distribution, less confidence. So that's the idea. Okay, so what we're doing here, we are reloading the previous ones. Okay, which I think I did here. Let me check. Okay, so these are the previous ones that are here. Okay, and then we are going to define the activation. Once again, it was the ReLU SILU, the encoder. And this is basically the same thing as before, right? The features, lifting the features from 2-dimensional to higher dimensional. And also I'm going to use some sort of simple function to create data points that were not in the original set. So we want to make sure it's out of distribution. Outside the training set or validation set. And of course, you use the same scalar. So it's the mean divided by the scale or range. And then you do the encoder. So encode with model, essentially, you take the encoder, which we save from the checkpoint. We put the input. Okay, if you have batch size, we can put a batch size. And essentially, you run a forward pass and you get it back. So it's very simple. Super simple, right? Okay, so what we're going to do here is that okay, so in this point, what we're doing is we load the checkpoints and reconstruct the encoders. So we load the previous points, we reconstruct the encoder with the store input dimension, latent dimension activation, and okay, there's some security exceptions for now, which is you have to trust loading models. Okay, let's not talk about security now. But in the current run, so the loader metadata is this, right? So you have the for blobs, we have the CDO as activation function, input dimension, latent dimension. This was the best epoch that we saved, and this was the test accuracy that we saved before, right, from the previous run. So this is just to make sure that we have reloaded the previous checkpoints. And then we're going to generate these new unseen base points with a new random seed. We apply the same feature lift, so they match the dimension. We apply the scalar from the checkpoint. We encode them to obtain the latent vectors z, and then we do a downstream classification with some sanity checks. Okay, so and this is how you should put this in production, right? Effectively. Okay, so what we do here, this is the energy and prediction, and I'm going to iterate over these 3 data sets with the unseen seed and the number of unseen points. Well, essentially, I do a bunch of stats. So if we run this first, okay, we have the data set, which was blob. We know the test size, the accuracy, once again, for the K and N. For the K nearest neighbor. And then we plot all this the energy for test and OOD. Let's check some charts first. Okay, so let's look at these charts. So we have the data sets, blobs, moon, and circles, same as before. And we have the downstream classification, right? So what we do is we take z as the vector, and then we calculate for each data set, we calculate the accuracy, right? So you have the 5 nearest neighbor accuracy on z and the prototype accuracy on z. Okay. And I forgot, I went too fast. So let's go. Let's roll back a little bit. In terms of downstream, we are going to use in this loop, we are going to use this a 5 nearest neighbor classifier on z, exactly as we did before. So we choose 5 as nearest neighbor. Always use an odd number. Remember that. And we are going to predict this and calculate the accuracy on the test set. And so this classifier it's for essentially for a new data point. If you remember, it finds the 5 closest neighbors in the latent space from the support, which was the training data. Okay, so this is how the nearest neighbor worked, and it's still the same concept. And so you then assign the new data point to the class that is most frequent among these 5 neighbors, right? So you might have like 5 positive, 2 negatives, and this says 5, right? And so essentially, it's essentially memorizing the training set, and it's just going to find the closest points and find the labels that belong to that one. So this is the kind of most like naive classifier you can build, and requires you to have the original training set, right? Because you have to go and look back the closest points. But we are doing this in latent space. The prototype classifier instead is essentially first is computing a prototype, which is the mean in this case for each class in the latent space from the support. So support is the training data. So every time you classify a new data point, it measures the distance from the points latent representation to each class prototype. So it's basically kind of like k-means, right? And then you find the data points that is assigned to the class which has the closest prototype, right? So it's actually a centroid based approach. So think of prototype is essentially a centroid clustering, and the 5NN classifier is essentially the nearest neighbor. So in terms of decision boundary, the prototype classifiers create usually these kind of linear decision boundaries, like Voronoi decompositions, whereas usually 5NN or any number of NNN of nearest neighbor creates more like non-linear decision boundaries, because essentially they go and carve the similarity from the original training point. In terms of computational costs, we know that the prototype classifiers are generally faster at inference because they only compare to a few prototypes, but neighbor always requires compute distance to all the other ones. The other things I mentioned was the robustness to outliers. So the prototype classifiers can be more sensitive to outliers if the prototype is simply the mean, whereas the nearest neighbor is somewhat more robust as it considers multiple neighbors. And usually, as you increase the distance, you get maybe a little bit of better, let's say, generalization. But then you then might be too far, and there's a trade-off, right? So yeah, so what we do here, we have two downstream tasks, and we run this energy sanity test. So we compare the median energy on the test points versus like random faraway points, and so we want this the OD mean median energy to be higher, right? So that should be the kind of expected one, right? So if we are so if they're very far away from the original points, the median should be higher. And so if you look at these results, you see that the 5NN accuracy is 0.99, and this is the accuracy of the prototype is a bit lower. And the energy gap in this case is the OOD minus the test is around 8. And you can see how this thing changed. So in moons, this gap is higher, and in circles, it's even higher. Okay, and then we essentially plot them here in this case. And well, the other things is that we also want to have the latent standard deviation is positive, and so these kind of simple checks are passed for all the data set. So we know that we are essentially not collapsed. So in terms of performance, if you look at blobs, moons, and circles, this KNN is the best one, so it's giving you like really good results, and the centroid is a little bit lower. And for the energy sanity, the kind of median OOD test, well, the energy gap is increasing, and well, the reason for that is, as you can see here, it's probably related to the complexity, because blobs was, if you remember, was 2 to 4 dimensions, moons was lifted to 8, and circle was lifted 12. So I don't think this is like a big surprise, but essentially there's something that you would see, which kind of makes sense. So the latent spread sanity checks, they are kind of healthy. So you have like some positive numbers. Blobs and moons are very similar. Circles jump a little bit, so that means we are not seeing a collapse. And well, I think in terms of kind of, if you want to summarize this, the classification gives us the utility. So like how good is data to give us this downstream task performance. The energy kind of tells us the confidence, or the, let's say, the novelty of the signal, and the spread tells us like this the health of the latent. So I think in general what we should do is sanity check for inference. Essentially use the same transformation scaling that you use during training. Make sure that the latents are finite so that they don't explode. So if they're exploding, that's a bad sign. Check the latent spread. It should be non-zero. If it's going to zero, like, yeah, that's very suspicious. You're probably having a collapse. And then look at the energy behavior. So essentially, these OD points should have higher energy scores than in distribution points. So this should be essentially, yes, if you're looking for some points that have never been seen before, that are very, very far away, this test should give you, this energy gap should give you like a number, like a positive number, right? So yeah, and this is essentially what I plot here. So you plot, you have the accuracy, the deviation for the latent, and then we have the mean energy test for the actual OD. And I didn't plot this. I should have plotted this. I think this is interesting because I did it for the for the test and the OD, and you can see that, yeah, there is kind of a big gap there. And just one more details on this chart, because that's probably something that it's not easy, like in practice wouldn't be always possible, but if you remember when we split the data into train, test, and validation, you can definitely use the median energy test. So this is the median energy score for the unseen test data. So this data was generated from the same distribution as the data that the model was trained on, but the model haven't seen it before. Okay, so the test energy, it's the typical confidence level of the model on data that it should be in distribution. So the median energy test should be unseen data but in distribution. The median energy OD out of distribution is, and maybe I wasn't clear, is the median energy score for out of distribution data, meaning that this data was generated to make sure that it's far away from the original model. Okay, so the original model, if you remember, it was moon, blobs, and circles, which you can you can generate as many as you want, but the way you should generate this or this, like something totally random that doesn't belong to that shape or distribution. Okay, and so this should be really like it's a good sanity check because it should be really high. I mean, like like if you put something, like it's like you're watching a TV and all you learn is about, I don't know, cats or dogs, and suddenly I don't know, you have an elephant, and okay, maybe there are some structures between animals, but if I show you, I don't know, a plane, that should be really out of distribution, and the energy, median energy, should be really high, right? And so well, the idea is, you do the difference here. I mean, I could have plotted both, but the difference is kind of to show you this gap that you should see, right? Especially higher dimensions, cluster dimension ID should be able to. It's easier to find points out of distribution. So yeah, this is very important. It's kind of like a sanity check. Once again, it should always give you higher, really higher gap. And so it means like the model has learned something, right? It's able to distinguish like what's in distribution and what's out of distribution. So with that, I'm going to close this one, and I think on the next tutorial we are going to do, maybe we're going to work on images or something a little bit more intuitive, or more geometric, so that maybe you can have a better understanding of how these things work with a more familiar data set, or useful. So thank you for listening, and see you in the next tutorial.